Hello, hope you're doing well today. I'm going to be doing another project Euler problem here, number 23. Got the answer there, 4179871, but I'll go over it here. A perfect number is a number for which the sum of its proper divisors is exactly equal to the number. For example, the sum of the proper divisors of 28 would be 1 plus 2 plus 4 plus 7 plus 14, 28, which means that 28 is a perfect number. A number n is called deficient if the sum of its proper divisors is less than n, and it is called abundant if the sum exceeds n. 28 is perfect because the sum of divisors is equal to 28. If the sum was less than 28, it would be deficient. If the sum was greater than 28, it would be abundant. As 12 is the smallest abundant number, where the sum of its factors is greater than 12, it's 16 if you add them up. The smallest number that can be written as the sum of two abundant numbers, so 12 and 12, is 24. By mathematical analysis, it can be shown that all integers greater than 28123, 28,123 can be written as the sum of two abundant numbers. However, this upper limit cannot be reduced any further by analysis, even though it's known that the greatest number that cannot be expressed as the sum of two abundant numbers is less than this limit. Find the sum of all the positive integers which cannot be written as the sum of two abundant numbers. So a little confusing wording here. I think it probably could have been worded better, but the sum of all positive integers that cannot be written as the sum of two abundant numbers. So since the problem states 28,123 can be written, well, all integers greater than this, so 28,124 and above can be written as the sum of two abundant numbers, we can effectively use 28,124 or 123 as the upper limit for our problem. We want to find the sum that cannot be written as the sum of two abundant numbers. So any number that is greater than this can be written as two abundant numbers summed together. We don't want to include those, so we don't really need to go past this number here. That's basically what this line is saying. A little confusing, but we can use this as basically the upper limit in our calculations. So I'll get to the code here. We will still be using, of course, the standard IO header to print out our stuff, but also for this and going forward, I'm probably going to be using the standard int header just to get standard sizes for variables, for integers, really. Make it a little bit more clear how large a variable is. You want 16 will be 16 bits, so up to 65535 for an unsigned, 32 for 4 million or whatever. So I just use that for me when I'm reading, code later on, be like, okay, I made this a 16-bit integer because I know it's not going to be above 65,000, say. That's mainly why I'm using that header, just to make it clear for me down the line. But since our problem gave us that limit, we can use that as, a limit, 28,123 or 124. I'll use 123 for this. Okay, so we'll have our main here. Don't need to return 0 at the end, even though we put int. Implicitly, once you reach the end of main and the brackets, it'll return 0 by default usually, so I'm not going to include it. For our variables here, I'm going to make a 32-bit, just in case. I'm going to call it sum of divisors, because we want to get, basically for each number we run through, we want a sum of its divisors, and if that sum is greater than the number, then we have an abundant number. I'm going to have an array that holds all of our abundant numbers. So since our highest number is going to be 28,000, I can make this 16-bit because it's lower than our 16-bit limit of, 65,535. So I'm just going to call this abundant numbers. I think when I was testing this earlier also, the maximum amount of abundant numbers I found was like 6,946 or so, something like that. So I just made it 7,000 for an even number. That's just, an arbitrary limit for our array here. So I also need an index for that array, so I'm just going to make an index here of I can call it ab index, abundant number index, just idx, just I, it doesn't matter. I'm going to call it ab index here. I'm going to initialize to 0. Okay, and then what we're going to have is I think this one can be 8-bit actually. I'm going to have an array that basically represents whether a number is the sum of two abundant numbers or whether it isn't, because at the end we can just go through this array and say, okay, we reached this point, it is not the sum of two abundant numbers, let's add it to our final answer. So that's what this thing's going to be. We'll call it sum of two abundant numbers. Sum of two abnums. So I know it's long, but this thing, we'll do limit +1 because C is 0 based, and I'm going to initialize the whole array to 0 as well. I mean, you'll see later, but this will basically hold a 0 or a 1, or you could include standard bool and make it initialize to like false or true. But basically this is going to hold a bunch of 0s or 1s, and if it's like a 1, it's going to say, okay, this is the sum of two abundant numbers. If it's a 0, it's not, and we can go through and add those numbers up at the end. So that's all I'm doing here. All right, then the last thing I'm going to put is the actual final answer that we get. So I'm going to call it sum of array elements, for lack of a better term. I could call it answer though, but I'll just call it sum right now. All right, so our main computation here, since we can initialize variables within a for loop within the scope, I'm going to do that. So I'm going to call it I. I could call it n or number though, but I guess we'll call it I. If it's not readable, I'll change it. I less than the limit. Oh, we want to include. Since the problem said integers greater than 28,123 were going to be the sum of two abundant numbers. It didn't say including, so I'm going to include 28123. Whether I need to or not, I'm going to include it, because it only specified numbers greater than this. All right. Oh, we can start at 12 as well. I don't have to start at 0. 12 is the first abundant number we get to, so let's start at 12. That makes it imperceptibly faster, skipping the first 11. But for each number we run through, first we want to get the sum of divisors for that number. So how do you do that? We basically, well, we're going to make another for loop here. And call it j. We'll start at 1. We could start at 2 though. Yeah, that's better. We'll start at 2. But we need to get all the divisors for a number and then sum them up. So to get all the divisors for a number, you could start at 1 and go up until the number. I'm not going to be doing this, but you could do this. It would be a little bit slower though. Can't type. Can never type when I'm talking. But the better way to get a number, well, let's just type this out first. We can check if I modulus j is 0. So if our number is evenly divisible by a number up until that, then it is a proper divisor. So, if we're starting at 12 and we're going to 1, 12 is divisible by 1 evenly. There's no remainder. So that technically is a divisor. If we go to 2, 12 divisible by 2, it's 6. It's evenly divisible. So this will be true in this case. But this means we found a divisor. Okay, and in this case, we'll say we found a divisor here, so we want to add it to our sum of divisors. So plus equal j. And then really we can check if our sum of divisors is greater than our original number. If so, we found an abundant number. So in this case, we want to add it. Found an abundant number, let's add it to our array of abundant numbers, our abundant numbers array. So we'll do abundant numbers, we'll start, we add an index for that. And this will equal our original number. So 12 is an abundant number. It is the smallest one. And at this point, so we don't have to keep checking things, we can break the loop here, break it a little bit early, so we don't keep going through the additional divisors if there are any. You can do this, it'll be a little slow though. A better way would be to look at it where the factors for a number, or its proper divisors, are basically sort of evenly distributed above and below the square root of a number. So I don't know square root of 12 off the top of my head, but we can check for, the factors above and below the square root of number, and if the one below is true, then we can also add the one that's above the square root. But you can go 1 until the square root of the number, or an easier way without including the math libraries and things, we can just do check j squared or j times j here. So check if a number squared is going to be less than, well, or equal, going to be less than or equal to our original number. So if we start at 2 here, 2 times 2 is 4. 4 is less than or equal to 12, so we know this is going to go through. We'll add 4 to the sum of divisors. Well, we'll add 2 rather. 12 mod 2 is true because it equals 6 with no remainder. We'll add 2 to the sum of divisors, but after this, we don't have to worry about perfect squares if we do it this way, which is good. But after this, we want to check if we found a factor, and if we want to make sure it's the one that's below the square root. We want to get the other one that's above the square root. We can check if our number is less than. Check if our factor is going to be less than the original number divided by that factor. So if we start at 2, this is going to be true. 2 is going to be less than 12 divided by 2. So since that is 6, 2 will be less than 6, but we also know that 6 is a factor for 12, so we want to add that one as well, and that's all we're going to be doing here. We want to add 6 to the sum of divisors, so we're going to add I divided by j, and that'll take care of the other one. So 2 in this case would be the factor below the square root, 6 would be the one above the square root, so we're going to add both. The next run through, well, this is going to be 2 plus 6, so this isn't going to be true, so it'll go on, it'll go to 3. 3 times 3 is 9. 9 is less than 12, or equal. 12 divided by 3 is 4, so this will be true. We'll add in 3, so it should be 2 plus 6 plus 3 is 11, but 3 is also less than 12 divided by 3, which is 4, so we'll also add in 4. So after this runs through twice, at least for 12, we'll have said the divisors are 2, 3, 4, and 6. And then the only divisors greater than that are going to be, 12, and then there's 1. We don't really want to count 1. Or 12, even though it's equal to the number. But we'll add all those. 2 plus 3 would be 5. Plus 4 would be 9. Plus 6 would be 15. 15 is going to be greater than I. Well, this will be true. It will add in 12 as an abundant number, and then we'll break. Hopefully that made sense. I know I'm not the best at explaining. But after this, we run that through for 12 and everything up to our 28,123 limit. We'll have found all of our abundant numbers in this problem space, so we can end. So after this for loop, after we found all of our abundant numbers, we want to, any sum that we get, the sum of two abundant numbers, we don't want to count as part of our final answer. So that's just what we're going to do in this next section here. So how do you get the sum of two abundant numbers? Since we have an array of all of our abundant numbers, we can run through the array twice and just add up all of those. So simple, basically a nested loop is what we're going to do here. Since we can reinitialize things, since variables are scope based, that's always good. We'll run through 0. We don't have to run through the whole 7,000 limit. We can just run through our index of numbers we found, which is going to be below that limit. I++. So we're going to make 2 loops here. Can't type, it's all right. I'm going to make I and J very descriptive, of course. Maybe you should do better descriptive names and not just generic index names. Probably be easier to read. Let's replace that as well. Okay, so if we're going to run through everything, we want to add them both up. So I'm going to have a statement here, though, to check that. If our abundant numbers I added to abundant numbers j, so if the sum of two abundant numbers in our array, if the answer to that is, well, the result of that is less than or equal, if it's up to the limit that we set, so 2, 8, 1, 2, 3, out of all of our abundant numbers, we kind of want to say that that number that we got, the sum of these two, is the sum of two abundant numbers. Since we have an array called sum of two abundant numbers, we can set that on. That's what I'm going to be doing here. So if that's on, we can say sum of two abundant numbers indexed at basically the sum that we just got, which is abundant numbers I plus abundant numbers j. Again, it's a lot of typing, but I think it explains it a bit more. All right, that we're going to set to 1. So this is saying we can basically loop through all the numbers from 1 until our limit, and every number that is a 1 we're going to skip, because that signifies that it is the sum of two abundant numbers, and we want to add up the numbers that are not the sum of two abundant numbers. So we're setting all those here, and that's pretty much it. Then we can just sum up all numbers that are not the sum of two abundant numbers. So another for loop, our favorite friend. We always love for loops, of course. I equals 0, I less than our limit. Since we're going up to 2, 8, 1, 2, 3, I'm going to make the limit 1 extra because C is 0 based. For indexing, of course. So for this, let's put our if statement here. So we're going to run through our sum of two abundant numbers array here. So if sum of two abnums index I, if it's 0, then we want to count it. Since we set all of the sum of two abundant numbers equal to 1, in this array. We just have to check for the ones that are 0. So if it's 0, then we can add to our final answer, which is going to be our sum of array elements. Maybe I could just call it answer. That might be easier. Let's just do, let's do that. Let's call it answer. All right, answer plus equal I. So for every number from 0 till our limit, or 1, we can make it 1. 1 until our limit. We're going to add it to our answer, because that is every number that is not a sum of two abundant numbers. And then after that, we should have our final answer. So I'll print it out here. It's going to be unsigned. And we'll have it. That should be all that we need to do for this problem. So pretty short. So if I typed everything in right, we shouldn't have an issue. There is no 223. So there we go. And we can time it and check the answer. That is not right, of course. That is very incorrect, so we don't want that. What did I do wrong? Let's put extra parentheses around these. I think that was not counting, maybe. Oh, yeah. Our sum of divisors, sorry. I always overlook things, We want to reset the sum of divisors on every iteration, or else it's always going to be true, and it's always going to keep adding up. So yeah, we want to Duh. I always forget the simplest things. Yeah, we want to set this to 0, reinitialize it on every time so that we get, the correct sum of divisors for the next number we're running. Of course, we also want to increment our index to make sure we're going into the next array element. That should be the only other glaring issue we have here. While I did have extra coffee today, obviously my mind is not up to snuff, and you do tend to forget minor details when you're trying to talk and do this at the same time. That's my excuse, and I'm sticking to it. So fingers crossed, 4th time, I think, is going to be the charm here. There we go. It does run pretty fast on this. Now, this is in a virtual machine, which it has 2 cores out of my 8-core CPU, and I think 2 gigs of RAM. So we'll say this is a dual core machine running at 3 something gigahertz with 2 gigs of RAM. It takes 0.2, 0.3 seconds, and that's not optimized. We can check it with maybe O2 or O3 and see if it goes any faster. So that, that cuts it down. 0.1 second. That's not bad, I don't think. 417-9871. Which is here, 417-9871. So hopefully you learned something or you enjoyed it. Not a bad problem. So just getting all the sum of divisors. You can get the divisors or factors for a number by going up to the square root. You add all those up, get the divisors above and below the square root, and if the sum of those is greater than the number, it's abundant. Add it to the array. Get all the sums for those, and set a flag basically that says, is it the sum or is it not the sum? And if it's not the sum of these two numbers, add it to your final answer, and there we go. So pretty simple. But all right, hopefully you enjoyed. Eventually I'll get to number 24, which will be lexicographic permutations, which sounds like a Mars Volta album. But yeah, I'll see you then. Thanks for watching. Appreciate it.